Thanks to all of our speakers, faculty, and panelists. I encourage you to turn on your video and unmute yourselves. We are very excited to be able to start this discussion, and I encourage our attendees to utilize the Q&A box to post questions. We had a lot of conversation yesterday about rare events, low prevalence, safe exploration, that sort of thing. And so it would be wonderful if anybody has those sorts of questions for us to get additional feedback on that. We are joined today by the three faculty speakers, as well as Jerry Lopez, who's the Trusted Autonomy Researcher with GE Research. Jerry has been at GE for 13 years, working on many projects involving safety critical systems. His primary research is in the area of avionics and air traffic management. And recently, Jerry has launched the Trusted Autonomy program, which looks at how non-traditional software applications such as ML and AI could be introduced into systems that require DO 178 certification. Jerry's also been collaborating with the Center for AI Safety for the past 2 years, performing research on applying formal verification to deep neural networks and looking at novel mathematical methods for analyzing safety properties of complex software algorithms. Welcome, everyone. I think maybe to get things kicked off and give our attendees time to write in their questions, it'd be great to hear from you all about what you think the current state of the art for AI safety is and where are we going next. Maybe we'll go in the order of our presenters and start with Mykel.
Yeah, sure. So I think one of the really exciting areas to me are the emergence of these tools for finding failures early in the design process. So the state of the art now is we're able to find failures in systems like ACAS-X and TCAS. We're interested in seeing how this can scale to automated driving problems where we have more realistic sensor error models for LiDAR and radar and so forth.
Dorsa, what about for your research? What's the state of the art in your area and where is it going?
Yeah, so I think it's interesting to think about this over the past couple of years, like what has changed and like how our views on AI safety has changed and all that. I think one thing that at least like I see in the robotics field and in the driving field also is that we've started like making a lot of like improvements and verification tools and all that for each one of the components. And we have started thinking about how these components are coming together. So I think we have made advances for each one of the systems, right? Like each one of the systems trying to verify that, trying to prove something about it. But also like from an overall perspective, like system level perspective, how these systems are coming together, like what are their relationships, what are their interconnections, and how can we make like an overall safety statement? I think there has been a lot of advances around that, and that's really exciting. I think another change in the viewpoint that has happened, at least in the field of robotics, is that we can't prove 100% correctness a lot of times. Like we have to fail. Like a lot of times, like there is going to be some failures. So if we do that like change of mindset that, hey, there is going to be some failures at times, then how can we live in that world? How can we minimize that? How can we do self-diagnosis? How can we monitor for these types of situations that are going to come up? How do we do repair? Like what if I fail and how do I do repair and come out of it? So I think those are really like exciting areas to think about. For my own research, I'm very interested in human-robot interaction, understanding humans. And I think it's exciting to bring in inductive biases about humans, like as I talked about it in the talk earlier, like how do we incorporate some of these biases and knowledge that we have in our learning models to better learn and better like understand what happens in like near the end of the risk spectrum or like near accident settings.
Clark, what about for you?
Right. So yeah, I'd echo what Mykel and Dorsa said in terms of the broader AI safety landscape. I think we have to have, multiple approaches. We have to be able to tolerate that things aren't perfect and so on. In terms of, the more narrow area that I'm focusing on, which is formal methods for AI safety, I think it's useful to do a comparison with how formal methods has developed in other areas like hardware verification or software. So in the beginning, it could do sort of toy examples, and then, you know, over a period of years, it would just keep getting better. And I think that's what we're seeing here. So I would say, you know, we're a little bigger than toy examples now, but we're still, you know, can't handle the state of the art type networks. But methods are scaling, I would say, by an order of magnitude every year. And I would expect that to continue. So what you can expect, I think, in the future is that these formal backends will become more and more powerful. You'll be able to use them on larger and larger networks, and they'll be able to do more and more. So that's exciting, but, you know, we're not going to scale to millions of nodes probably right away. So that's kind of where we are.
And Jerry, thanks again for joining us. What are your perspectives from industry? What is the state of the art today, and where do you think it's going? What's sort of the biggest thing you're looking forward to seeing in safety in the next year or two? Oh, you're muted.
Yeah, sorry, I muted myself. Thanks. So I do want to echo, you know, the comments that were made by Mykel, Clark, and Dorsa, and just let me start by saying that it's been a real pleasure working with the Stanford Center for AI Safety and getting to know some of the research that's going on for ensuring or at least building more confidence in AI based systems and safety critical applications. So, you know, first talking about what Mykel was addressing, where, you know, one of the challenges with learning enabled systems is the state space is just so enormous that, you know, traditional techniques for doing code coverage and that sort of thing simply don't scale. And so, you know, some of the techniques that Mykel and team are developing around, you know, using machine learning to adaptively explore these enormous state spaces and zero in on failures and very importantly, rare failures that you wouldn't find otherwise with just traditional testing, I think are very important. So again, you know, this notion of being able to adaptively explore these enormous state spaces is really important. And then, you know, with the work we were doing with Clark, where you can take a neural network, for example, and you know, prove bounded behaviors over some, you know, hopefully all, but large portions of the input space, I think is enormously important as well. So we've been very, very happy to apply these techniques, you know, to some of the real world problems that GE is facing. But that's really on the tool side, I would say. You know, this notion of being able to generate evidence about the safety of your AI-based system is really important. Where we're really starting to look at now is, you know, that's really only half the problem. You can generate all of this evidence and, you know, generate all of these artifacts about a learning-enabled system, but that's really only half the battle, because you also, you know, in the real world have to convince a certification authority, you know, that the level of trust in your system, you know, exceeds some threshold. And that's kind of where we're going with GE right now is, you know, in addition to continuing to, you know, have interest in, you know, the types of tools that can, you know, explore and you know, prove the bounded behavior of AI-based systems, we're starting to look at, you know, how can you build an assurance case that a certification authority will have confidence in about the state of your system. So we're involved in a couple of DARPA programs. One of them is called DARPA ARCOS, Automated Rapid Certification of Software. And the idea there is, can you assemble the safety artifacts that you've generated about your system and then build these large assurance cases using what's called graph structuring, you know, GSN, graph structuring notation, goal structuring notation, sorry, to generate these views about the safety of your system. So again, I think we're pretty excited about some of the advances in you know, some of the areas around building assurance cases and automating the assembly of assurance cases.
So we have a few questions in our Q&A box, so we'll jump in there and maybe answer some of these more technical questions that we've seen so far. We see one, I am encouraged to see the work on AI safety. Could you please comment on how this relates to the idea of, and I'm going to mispronounce this, Lyapunov stability in adaptive Lyapunov, thank you. I knew I was going to get it wrong. Stability in adaptive dynamical systems. Mykel, do you want to start since you know are familiar with
Yeah,
that?
and then maybe Dorsa can add to it. We have been looking at the idea of using Lyapunov stability to analyze the use of a neural network controller in a closed loop system. So at the start of our collaboration with Clark's lab, we were just interested in proving fairly simple input-output properties about the ACAS-X network and some other networks. But what we're really interested in is if we follow that guidance in a real system, can we prove that we will be safe? So the outputs of the network, those are going to generate some controls, right? And the relationship between the input and the output is of course going to be very, very much non-linear. And we want to integrate those controls with a model of the dynamics, because as we execute those controls, it's going to change the state of the world, as well as the inputs to the neural network at the next state. So Lyapunov theory allows us to prove some properties about if you're within, for an example, if you're within a safe set, will you always stay in a safe set? We've only just barely started going down this route. I know that one of Marco Pavone's students has been looking at this. Marco is another faculty associated with the Center for AI Safety. But this is still early days, but I think that's definitely an exciting area of research. Did you want to add anything to that, Dorsa?
I think that was very complete, but just like maybe like one sentence like on top of it. Yes, I think Mykel kind of like talked about it already, but the Lyapunov stability is only going to give us one form of safety. Like there are different forms of safety that one might be interested in depending on which part of the system you're looking at. And it is definitely like a useful tool to use, and we definitely like use it as Mykel was just saying. In our work, we are looking at multi-agent interactions these days, and what sort of equilibria like the agents end up in, like in multi-agent, through these repeated interactions, multi-agent interactions, like looking at it game theoretically. And we're using Lyapunov stability and tools from Lyapunov stability to ensure that the equilibria that we're reaching in is going to satisfy a set of properties. It's really useful, but it doesn't like give us like all the properties you're interested in, or it can't be used at all levels of the system.
Maybe that's a good opportunity to address one of the other questions that we have from the audience from Ricky Ho. How do we restrict reinforcement learning exploration with safety in mind? And can you share what the general approach is on that? I know that safe exploration is a big element of the research efforts in AI safety.
So I can maybe continue on that, and others can of course add after. So one common way to go about this is to think about the safety set that we have and having uncertainty around it. So taking like a Bayesian optimization type of approach, a safe Bayesian optimization type of approach. So you might have an objective, or you might have a constraint, that's your safety set, and you're not sure about it. So you basically try to define some sort of uncertainty around it. And as you explore, then you try to basically reduce that uncertainty and at the same time optimize your objective or satisfy the constraint. And that goes back to this thing that, hey, if I have like a hot like object here, I like want to go around it. Of course, I don't want to touch it, but if I'm really uncertain about like some region in the environment, I might end up like kind of like poking it, and like I need to poke it to like reduce my uncertainty that this is like a hot object here. So that's kind of like one common way of going around safe exploration, safe learning, using like this Bayesian optimization approach, defining uncertainties and reducing uncertainties by exploring the most uncertain and the most useful like samples from the environment. Mykel and Clark and Jerry, you guys can add to.
Yeah,
that was great.
I thought that was perfect.
Jerry, any insights on the sort of real world implementation challenges of these sorts of safe exploration? Are we close?
Well, again, how do you define close? Nobody's really gotten there. I mean, if you climb a tree, you're closer to the moon, but you still got a long way to go, right? So again, one of the challenges is going to be maturing some of these techniques to the point where they can start making their way into, standards, for example. I think a really good example of the journey from sort of novel techniques to, these techniques getting adopted in real certification activities is what Mykel was talking about earlier, adaptive stress testing. Because if I'm not mistaken, Mykel, you mentioned that adaptive stress testing was applied to the ACAS X or ACAS XU or ACAS X?
ACAS X, yep, as well as XU, yep.
Okay, right, ACAS X. And did some of the evidence that was generated by adaptive stress testing on ACAS X eventually make it into the certification case for ACAS X?
It was definitely part of the discussion, for sure.
Okay.
One thing to clarify with ACAS X is that it's not doing any real-time exploration. So the concept there, as well as the concept, I think, in most aerospace applications, is you do all of the learning and training of your control strategies, decision-making strategies, you do that all offline. And then you freeze it, you go through the certification process, and then deploy it. In the context of safe exploration, that tends to be more relevant to probably the robotics applications that Dorsa has been working in. It's also relevant to making movie recommendations through Netflix and so forth. I guess in some aerospace applications, like if there's like a semi-catastrophic failure to your aircraft or spacecraft, and you have to kind of learn on the fly or adapt on the fly to recover the aircraft, then maybe this might be relevant. But you can still use the adaptive stress testing framework that we've been using for ACAS X and other systems to assess the ability of our systems to successfully adapt on the fly safely.
So we talked a little bit about safe exploration, as well as, the ability to fail, I guess, and assess those failures. Are those the sort of main challenges for building and deploying these trustworthy autonomous systems, or are there others that we need to consider? Maybe start with Clark.
Can you just say those two challenges again?
Well, we had talked a little bit about safe exploration as well as, reducing failure rates. But the question is just a little bit more broadly, what are the main challenges for building and deploying these trustworthy autonomous systems?
Yeah, so I think those are definitely big challenges. One that comes up in the work that we're looking at that I'd like to highlight is what I call the specification problem, which is, what does it mean to be safe, right? And so, in some cases, it is easy to say, like you can say, oh, this particular parameter needs to be within this range or something. But in other cases, and especially when you have these learning components, it's very difficult to say what it means to be safe. Like the best you can do is some very high level property, like, this car should not crash. But breaking that down into specifications on the system is very challenging. So I think that's a big challenge is how do we talk about safety in sort of a formal or a rigorous way that we can measure and evaluate, and in some cases you can, and in some cases we still don't know how.
So that's actually a really interesting comment. Yesterday we had a lot of discussion about adversaries and noise and situations where how do you tell if it is an adversary or if it's just a natural, realistic, valid outlier? And then how do we develop these algorithms that can be, or maybe define in regions? I don't know if you had any thoughts about that, about how your work could, help with that tuning of, how much risk from adversaries do we need to accept?
Yeah, maybe I'd like to hear what the others want to say about it too, but maybe let me also connect this to one of the questions online about, are we moving more towards constraints in safety or penalties? And I think the answer is all of the above and more, right? So you have to really, in order to show that a system is safe, you have to look at all of the possible failure modes, right? And this is very challenging. It's going to be as safe as its weakest link. If you miss something, or if you ignore something, then that's where an adversary or other problematic issue could arise, right? So I think you need to, do the best. We need to have research on robust training, on safe training. We need to have, ways of checking the systems after they're trained, both formal and informal. And we need to look at the system in a loop, and have ways of understanding the way the system interacts with its environment and the dynamics. So the answer is all of the above and more. It's a very, challenging problem. And, as someone who works in validation and verification, you just have to be paranoid all the time, because if you miss something, that's where the failure will be.
So maybe to build upon Clark's comments here, it's really, the challenge is about the space of edge cases. The space of edge cases in these systems that involve multiple agents, humans, and sensor failures. The space of edge cases is just so incredibly vast. So I think we can break it down into three major problems. The first one is, how do you model the space of edge cases? Not just like mapping out what kinds of sensor failures might there be, what kinds of human responses might there be, but also what are their likelihoods? Because of course we care more about more likely edge cases than less likely edge cases. So getting the model right is tough. The second part is, how do you build a system that's robust to all of these edge cases? And of course, we're all very interested in developing tools for that, making it robust to variability in human behavior and sensor errors. Then the third part is, how do you decide which edge cases do we care about when our system fails on them? And we've been working with GE and other partners on on developing tools for finding failures, but we need to figure out how to categorize those failures in a way that's human interpretable, so that we can decide, okay, so those failures exist. Should we do something about that in the design of the system? And in that process, we may have to make very difficult trade-offs between maybe efficiency and safety. And I think we really need to develop better tools for addressing that engineering challenge.
Jerry, any thoughts on edge cases and whether that sort of thing should be built into the model, or some follow-up on the things that Mykel was discussing?
Sure. So when Mykel was talking about edge cases, and in particular when he was talking about being able to model the interactions between the automation and the human response, the first thing that entered in my mind was the 737 MAX tragedies. And, the folks that were designing the safety systems around the, 737 MAX and, the pilot training and or lack thereof, I don't think they ever could have imagined the type of edge case where a pilot would actually be fighting the automation. So, a priori, how would anybody have ever known? I mean, I'm not making a case that, defending or criticizing anybody, but I'm just stating, how would anybody have ever thought to model that type of interaction? So, and obviously we see the tragic consequences. So, again, I think the ability to correctly model and understand these corner cases, I think, is critically important. And we're a long way from having everything that we need in that space. I'll pick up on another thing that Clark was talking about, and I would definitely agree that one of the big challenges in specifying what it means to have a safe learning enabled system is it's pretty easy to say, well, the car should never crash, or the car should never, hit a pedestrian. But actually going from that high level claim of safety and decomposing that into low level properties that you can then go and test and formally prove is enormously difficult. At the outset, it wouldn't seem like it would be that difficult to decompose a high level requirement like that into these low level requirements, but in practice, it's very, very difficult to do that. So just a couple of thoughts on that topic, Erica.
Yeah, I think maybe the fourth thing to consider after you decide which edge cases do we care about is how do you design a system that's can be rebuilt quickly and efficiently under these sorts of failure conditions. I know we had a lot of conversations about that being a big issue with the Boeing disaster was you can identify the problem, but then how do you actually rebuild and recertify quickly and efficiently? We have a question from the audience. Is it actually possible to quantify the trustworthiness of machine learning? I don't know if somebody wants to comment on that, either in an optimistic or pessimistic way.
Well, go ahead, Jerry. No.
Again, I don't think, it's an open question. And it's a question that really is only going to be answered by entering these systems into the wild and seeing how they behave. We can only explore so much of the state space and so many of the edge cases, and the more that we can explore before actually putting these systems out in the wild, the better. And that's kind of what, these techniques and tools that we're talking about in under development and AI safety are helping us to do. But again, I think Dorsa made the point earlier that you're never gonna make a system 100% safe, and that's true whether it has AI in it or not. Okay, you're never gonna make a system completely safe. So again, we learn by doing, and unfortunately, we're just going to have to accept that there will be failures in the field. One of the things that's a little frustrating, just as a side note, is I don't know how many Americans are killed in car crashes every year, but it's probably in the tens of thousands.
It's about 40,000, I think, Jerry.
Yeah, I was going to say 30,000, but your number sounds probably right. And we just sort of accept that as a society. And there's one fatality from a autonomous vehicle, and it makes all the papers, and it's somehow unacceptable. I mean, obviously it is unacceptable, but there's some of it is just culture change, I think. As the culture, more and more adopts and accepts the fact that, that no system is going to be failure free. So I'm kind of waxing poetic now. So I'll stop there and let Clark make his comments.
So just about the original question of can you quantify trustworthiness? So I think, it depends. So and again, it comes back to the question of what does it mean to be trustworthy? And can you give a rigorous definition? And again, in some contexts, you may be able to do that, or you may be able to give a rigorous definition for some part of it. And when you can do that, then we're a step closer to being able to quantify that and give some rigorous guarantees. But then another part of it will always be empirical, as Jerry says, where you have to test and measure and get some real world experience to see what the trustworthiness is. So it's a very tough question to answer that broadly.
There are certain aspects that we can quantify, like prior to the deployment of ACAS-X, we can estimate the probability of collision in different airspaces. But in terms of trust, whether the public will trust it, we're talking about the feelings of humans in their hearts, and that's a little bit tricky. But there's some interesting precedents. There's of course the story about elevators. So back during the early days, there were elevator attendants, and they were there to help assure people when they first started having elevators that things would be okay. And then there was a elevator attendant strike, I think in New York City. I don't remember what year, but people felt trapped for a little while, or they were a bit nervous, and then they saw that, oh, everything's completely okay. And now I don't think we see elevator attendants anymore at all, really. So I think that a lot of this is societal and has to do with perception.
Maybe we should dive down a little bit more into the history as well. We had a question from the audience about wondering if the exception guard rules start adding up, are we reinventing the issue that took down the expert systems back in the 80s? I know some of you usually have a little bit more history involved in your longer presentation, so a good opportunity to address some of those slides you didn't get to include. I don't know, Mykel, if you want to expand.
Yeah, so I think what's being referred to here is the expert systems movement that really dominated the AI approach, like in the 80s. So the problem with those systems were that they were largely rule-based and with hard constraints, and that ended up resulting in very brittle systems. And they're brittle because the assumptions made by those rules often don't, those assumptions aren't met in the real world. So there are, variations in human behavior. Like I mentioned, there are sensor failures. So if our rule depends upon perfect sensor information, we're likely to be disappointed when it's deployed in the real world, especially in systems like aviation systems, where we really need an exceptionally high level of safety and provide robustness. And building robust rules by hand is super tricky, really, really tricky. We saw this to some extent with TCAS, the predecessor of ACAS-X. So TCAS was originally developed in the 1970s and involved a very large collection of human-designed rules. Although TCAS has been a major success story, there are certain situations where it doesn't handle unexpected situations very gracefully. And that's one of the values of, one of the nice aspects of the newer round of AI systems that have robustness as one of the primary concerns in their design. So taking probabilistic kinds of approaches to modeling sensors and other agents. I would guess that Clark has things to add along there, and also Dorsa.
I wanted to just add on, like, again, a viewpoint thing rather than like a very specific thing. So I think, yeah, so coming up with rules and constraints is hard. That is true. Like, that was a problem with expert systems. That is a problem in coming up with specifications. That's a problem in coming up with reward functions. That's not solved. Like, that's a big problem. And then taking a fully like data-driven learning-based type approach also doesn't solve it. Like, as we kind of like have already seen the limits of some of these systems in many applications. And kind of like, if you think about where like these data-driven learning-based models are right now, like a lot of research is about trying to bring in structure and like inductive biases and constraints and like knowledge that we have, like robustness, like all of that during the learning process, because we kind of have hit the limit of just like learning and memorizing data and like figuring things out from data. So it is kind of interesting that we're seeing a shift even like there, trying to bring in some of these rules, some of these knowledge that we have in the learning process, because like that's like needed to make that leap, to be able to give guarantees, to be able to say, hey, this system is robust. Like that needs, like as Mykel was saying, right, that needs to come in the design process. And I think, yeah, we are way beyond like the expert systems, but we still need some of these structures, some of these rules. Like we can't like throw that out. Like that needs to be part of the system.
So adding to Dorsa's comment, so the value of having rules, that there's the inductive bias that Dorsa mentioned, but there's also the nice interpretability of rules, right? Humans can largely understand rules. Whereas if you have like a neural network or a big lookup table, it may be a little bit more complicated to kind of understand what's going on. And so interpretability, I think, is a very important theme that we're studying as part of the Center for AI Safety. But there's a lot more to be done along that line.
That was an interesting comment that was made in Andrew Ng's keynote on Tuesday, where he was saying they developed all this interpretability into a diagnostic support system for computer vision based radiology. And he said that the physicians looked at it once or twice and said, okay, yeah, I agree with that interpretability, and then never looked at it again. And so, you know, it's certainly something that's really important, but it takes a lot of work for probably, you know, somebody to look at it once or twice, say, yeah, I trust the system now, and then move on.
So there might be a difference here with like the certification processes for aerospace systems that are still really tied to these rule-based systems, you know, dating back, you know, many decades. Probably Jerry could maybe speak to that to some extent, where the certification processes are really at the specification level, and the specifications are normally these hard sets of constraints and rules.
Yeah, we actually had a question in the audience about how do you certify these algorithms as part of airplane certification. Jerry, I don't know if you have any comments or thoughts on the difference going from rules-based to you know, more machine learning or you know, more black box method.
Sure. So as many folks know, sort of the guideline for certification of avionics, you know, safety critical software is the DO-178 standard, and what that does is it sets out a prescriptive approach that says you have to go do X, Y, and Z processes on your system. You have to specify requirements, high level, low level requirements. You have to go do requirements-based testing, simulation, et cetera, and you have to generate a mound of evidence, and then you know, build a safety case that you then take to the FAA. And I'm not sure that that's all that different an approach to what you would want to do for a learning enabled component. I mean, what we've been talking about is doing a number of tests, you know, simulations and validation and verification, formal V&V. It's really all about, you know, generating an overwhelming abundance of evidence about the you know, what your system is going to do in all different kinds of situations. So I don't necessarily look at the process for certifying AI in terms of, you know, what sorts of artifacts you need to generate being all that different from, you know, what we do today with deterministic systems. Again, I think a lot of it has to do with societal and you know, cultural, you know, subjective ideas around you know, not really understanding what an AI system would do versus a, you know, like just a regular rules-based system. So again, I think just, you know, with time, I really liked Mykel's example of the elevator attendant. I don't know if that was Mykel or Clark that talked about the elevator.
That was Mykel.
Again, I think, you know, the best thing we can do is try to develop the tools and methodologies that are going to generate as much evidence as possible about how the AI learning enabled components will behave in as many possible situations, especially, corner cases and that sort of thing. And then, to the stuff that Clark is doing around, proving the bounded behavior and, doing the reachability analysis like he was doing with GE. I think is really important. But again, there's really no guidebook to how you're going to certify an AI-based system. We're kind of at the forefront. One of the things I find interesting, though, is the avionics industry is very similar to the autonomous vehicle industry in this regard, where the certification authorities just really, who have spent decades, developing these techniques for how to certify deterministic systems, they've kind of thrown up their hands and said, we don't really know how to certify avionics or autonomous driving software when it has AI involved. And so they're kind of looking to industry to sort of set, industry, you tell us what you think are the best approaches, and then we'll give you a thumbs up or a thumbs down on those approaches. So, yep, still very much a journey that we're walking, with the certification authorities, and there's a long way to go.
So this is kind of how about a fun exercise that addresses two of these questions. Let's imagine you could flip a switch and all of a sudden only fully autonomous vehicles were allowed on the road. Would that make the problem space less challenging? And is this something that could be, actually realistic from, a benefit to human impact? I don't know, any thoughts on that? Maybe Dorsa, you do a lot of these sort of interaction between autonomous drivers and non-autonomous drivers and actual people.
Yeah, so yeah, it would make the problem much easier. So, and then there's a lot of work around it too. So actually, like research, like there's a lot of actually older work around connected vehicles and like connecting infrastructure and like what information should be shared, and like if we can tell all the cars what to do, like we don't even need like traffic lights. Like there are all these videos of cars just like seamlessly going through each other, like knowing when to slow down and when not to slow down. So that would make the problem much easier. I think dealing with humans is pretty difficult. And actually, like trying to get to another question that came up at some point is the problem with humans is that they're not adversarial, they're not random either, and they're not like cooperative either. So they're something in between, and it's really hard to figure out when they are like really cooperative and trying to help you, or when they're competitive, or when they're somewhere like in between. And kind of like assessing that is really challenging. I think specifically for driving, that becomes really challenging. So why don't we just automate all roads? Because it's expensive. Like actually, like back in the day when people were thinking about autonomous driving, there was this question of autonomous roads or autonomous cars. And like we could have gone like either route, but just autonomous roads seemed so much change to the infrastructure, and there was like no reason to like spend that much money on like autonomous, like everything autonomous, like platooning cars, things of those form. But now that we see some benefits in autonomous driving, I do think we need to think about redesigning some of our systems. Like what is, like there's no reason to use like the vehicles the way they are, like as an autonomous car. Like we can change the design, we can actually start changing the infrastructure. And you're already like seeing a lot of research around that area too, and a lot of work around that area. Yeah, so I think that was kind of like just trying to answer some of the points here. Yeah.
Mykel, any parallels to aviation here where we have seen a
Yeah.
good amount of automation?
Yeah, so, and Jerry could probably elaborate on this, but things change very slowly in aerospace, especially commercial air transport. So even just getting aircraft to transmit their GPS locations, that was a huge deal. This ADS-B program, Automatic Dependent Surveillance Broadcast. The idea and that idea is super simple, but that was very involved. With ACAS-X, it's going to be a long time until, I mean, the release of ACAS-X will be gradual. It'll be over time. And in the meantime, ACAS-X is going to have to interoperate with the older system called TCAS for the foreseeable future. And so although it would be much easier if everything used the same system, was fully automated, removed the human, which is the primary stochastic element in the world. That's just not practical. It's not going to happen. And so part of the engineering challenge is interoperating with a mixture of other systems with gradually increasing levels of autonomy or and sophistication.
Add one more point. It kind of like tries to answer one of the other questions, I think. And that was this question of like, if you have autonomous cars on the road and human driven cars, like can the autonomous cars like guide humans towards like other like objectives and things of those form? That's again like an idea that I think is like in the research like infancy like part of it. I think it is a cool idea. It is possible to use autonomous because the cars are influencing each other. So it is possible to use autonomous cars to actually like guide like other drivers towards specific like roads or lanes or like to basically like maneuver to help traffic. I think that connects to another question, which was about who is benefiting here and who is losing, right? Like it's like almost like a zero-sum game here, right? So like like if someone is getting ahead, someone is getting behind, right? Like if the autonomous car is getting ahead and some human-driven car is getting behind, someone is losing here. So the question is like who is losing and who is winning, and what is the right objective? Like what would be the right societal objective that you would want to use? What would be the right like fair objective? So we had this work from a couple of years ago where we were looking at traffic and traffic congestion, and we were trying to come up with policies for autonomous cars that would help with traffic congestion. But that's not alone like a good objective, because like one person might take 3 hours to like get from one place to another place that would usually like 20 minutes, and maybe like 90% of people like will take 20 minutes. Is that like is that fair? That's not really like fair to like that one particular person who would take like 3 hours to take the same route. So coming up with the right objectives, so like best like fair objectives here, I think is also like important. And again, it's a specification question. What do you want to satisfy?
There was also a question about fairness from the perspective of different populations. Like, is it ethical to develop these systems that maybe make things way, way, way better for the average person, but maybe there are certain populations. This individual mentioned that what if overall autonomous vehicles are really good at preventing, deaths from, vehicle accidents or vehicle pedestrian accidents, but they're just terrible at identifying bicycles, and so they just, completely ignore them. Are there methods that are going out and identifying whether or not there's subpopulations that are being affected differently? Is this a major ethical concern?
Maybe I'll take a shot at that. One of the reasons why we grew the center over the past year to include folks like James and Tino is to have that as one of the central questions that we try to answer as part of this center. Just answering from the perspective of my lab, some of the tools that we've developed, like the adaptive stress testing that we've worked on with Jerry, one of the original reasons why we developed this in the context of automated driving was to identify during design time potential ethical issues that might arise. So one issue is we can tell the adaptive stress testing tool, what's the most likely situation where we have to break the law in order to save a life, or alternatively, where might we have to swerve into a car to prevent a collision with a cyclist. So sometimes when using the standard tools of just Monte Carlo simulation and collecting aggregate risk metrics, is sometimes we overlook some vulnerabilities for specific populations or particular situations. So disaggregating the data is quite important. We had to do this for ACAS-X. Like with ACAS-X, we weren't just concerned with a single number of probability of collision. We wanted to understand, like, did that vary at different altitude layers? Did it vary in different airspaces? Is it different in Europe versus the US? And separating out the statistics is quite important, but of course it comes at additional computational expense. You'll have to run more and more simulations in order to collect statistically significant figures.
Any thoughts from anyone else? I think we've answered most of the questions. I'm sorry to those people in the audience. We haven't been able to address questions yet, but I'll pause for a moment in case any of you want to comment on anything we've discussed so far, and then we'll go through and hear from you individually about what's next. All right, sounds like we're good on input on the previous questions. Let's start with Jerry. What's next for you and GE with AI safety?
Yeah, so again, we've been very, very privileged and happy to have worked on some of the hardest problems in AI, particularly with an eye towards exploring these large state spaces and proving bounded behavior of learning and labeled components. And I feel like we've only scratched the surface. A lot of our focus has been on some very narrow examples like the ACAS SXU and some of the flight management stuff that we did. And one of the things I see is what I'd like to do is to continue to explore these techniques on some of the same problem sets we've been applying them to, but to look at there's just like it's a very target-rich environment out there. There's a lot of problem sets that we could apply some of these techniques to. So one of my objectives is to continue to search for problem sets in the safety critical software area where people are looking at including learning enabled components and trying to apply these techniques. That's number one. And then number two is really starting to look at okay, now that you've generated this evidence about your learning enabled component, how do you then convince certification authority that your system truly is safe? And one of the methodologies there, one of the techniques there is to have some of these sort of researchy type techniques and tools get mature and make their way into into standards. I think that's one way that that we can mature that side of the problem. So that's kind of what we're going to be looking at, Erica.
Clark, what's next for you and your group?
Well, specifically, I think we know exactly what we're going to do, which is we're just going to try to grow the capabilities of these formal tools. And as we do that, we'll find that the set of applications that we can apply them to also grows. And so that's great. I think a little more broadly, though, I am interested in these questions of how do you sort of holistically approach safety. A formal approach is going to be one piece of it, but there need to be other pieces, and we have to be creative and smart. I actually do want to harken back to one of those earlier questions about expert systems. I mean, it's just amazing how much better today's AI systems are at being robust than those old systems. But of course, what happens is we got greedy, and now we tried to solve much, much harder problems, right? We're trying to solve perception and object recognition, and even in some cases, things that look more like general AI. So, the AI is way better than it used to be, but now we're really trying to push it. And I think we need to be careful and not push it too far too fast, especially in safety critical systems. Maybe take a little bit of a step back and try to make sure that the approaches we're taking have this have some strategies for how we're going to make it safe.
Dorsa, what's next for you and your group?
Yeah, so I think for us, like from the big picture, we are going to think about interaction a little bit like more carefully. So in general, some of the next steps that we're very excited about is thinking about algorithms for robots and autonomous systems that carefully think about interaction with humans and also with other agents, just more generally. And the approach that we are very excited about is incorporating some of these like inductive biases, some of the rules, some of the reward functions, robustness, control, like things that we get from control theory, and incorporating that in the learning process. So at the end of the day, we can have this agent that is taking data, but at the same time is satisfying a set of properties that we are interested in to be better interactive. And I'm in general interested in very difficult, like more challenging, like safety critical situations too. So I'm excited about exploring near accident driving scenarios where we have limited data and like humans are not acting like rationally, and thinking about that carefully. Another domain that I'm very excited about these days is assistive feeding. So when you have a robot and you want to operate the robot to like feed you and bring food to you, and even if you follow like the safest like policy there and like shortest path or whatever, like the person is really scared when like a knife or a fork is coming to their face. So like how do we think about that type of interaction, and how do we think about safety like in the space of robotics?
I love your other talk that has a lot of those failure videos with with feeding, and there's a funny turtle video that she often includes. So I encourage you guys to watch some of Dorsa's historical recordings. Mykel, what's next for you and your group?
Yeah, so I would say one major theme that we'll be pursuing over the next year or so, probably longer, is really hybridization of these different kinds of methods. So both the symbolic rule-based methods as well as the data-driven methods, kind of along the lines of what Dorsa suggested for building robust, reliable AI systems. But as well, I'm interested in the hybridization of verification and validation methods. I think a step in this direction you saw in the work of my student, Kyle Julian, that combined the formal methods tools, so like the Marabou from Clark's lab, with adaptive stress testing that allows us to build safety cases that we would not have been able to with just adaptive stress testing on its own, or with just formal methods on its own. And I think that's super exciting.
All right, I want to thank our panelists for participating in this discussion, and our audience members. I only made it halfway through my prepared questions, so we really appreciate all the engagement and questions that that you all post to us in the Q&A box. We're very excited to be finishing the second year of the Center for AI Safety. As I mentioned at the beginning, we've had over 63 publications since January 2018, and a new book coming out. So we're really looking forward to continuing to move the research forward, and then also provide educational opportunities for our members and the larger community.